everyone. How are we doing today?
Great.
It's
Excellent.
Great. Fantastic. It's really a great honor to be here and to speak with you all and to be in Korea. This is my first time, and I'm really enjoying myself very much, and I feel really quite honored to be here. And share with you a little bit about some of our developing standards in the United States and to kind of give you a sneak peek on some of the ways that we're looking at assessing some of these technologies. You'll see some things that fall in line from Craig's and obviously Tom's presentations here with what I'll present, talking about sort of how we are trying to standardize the process of looking at some of these hazard resilient systems. And so a quick outline of what I'll like to talk about today are some of the earthquake impacts, a little bit of background, sort of our development of a seismic design standard, and then also a testing standard on how in the United States we're hoping to move forward to assess some of these products. I start with a couple of pictures here from the recent earthquake in Turkey, where we were doing some reconnaissance work to try to understand the effects of earthquakes on pipeline systems in which were severely impacted. An example of a large transmission line here on the order of 5 meters in diameter, where there's a natural or oil pipeline crossing over the top of it, and the fault rupturing at an angle right about here. So the interaction of these lifelines, the performance of the gas pipeline, or the oil and gas pipeline did quite well, but the water pipeline did much worse, and it depended on sort of the orientation that the things were applied in, but there's some important lessons to learn. The other point I'd like to make is that while this is sort of based on seismic responsive systems, we expect a lot of the work that we're doing to be able to contribute to our resilience over a number of different ground movement scenarios, which have been pointed out a little bit earlier as well. And so if we talk specifically a little bit about our seismic hazards, we can kind of orient our pipes into two different general categories of deformation. We might have a pipeline that's crossing a ground movement scenario in a perpendicular direction that's going to produce predominantly bending or transverse deformation onto a system. And if we have a pipeline that is in somewhat parallel to the crossing, we would have maybe tension at one area and compression at another area. And so that's what I'll focus on here with our standard and the standard developments, and then I'll bring this oblique crossing back in just a little bit at the end, just to give you a sneak peek of what's coming forward. This is an overview of the last about 10 years of the hazard resilient testing that's gone on. And Professor Rowe talked about a number of projects that we worked on together at Cornell with a number of different types of pipe materials over time, looking at trying to assess the resiliency and the ability of these systems to operate. I am coming from the University of Colorado Boulder, where we've done a number of projects over the past several years, looking at additional systems and capacities. And then there's also the University of California, Berkeley, that's been doing some testing and will continue forward. This is really some of the research work that's gone in, and in parallel to that, we've been working with Dr. Craig Davis and others in the United States on developing a manual of practice for seismic design of water and wastewater pipelines. At this time, there is not a general guidelines on how you would actually design a resilient network, as we talked about a little bit, and so we've been working on that for quite some time. And as we've been working on that, we understood the need for a testing standard for us to be able to determine some of the capacities associated with these systems. So right now, we have a number of excellent ways of looking at the performance of pipeline systems that look a lot at internal loading. So that would be burst testing and long-term pressure, hydraulic-based design. We also look at material performance, but few of these things look at the pipe and the coupling in terms of how it might respond to larger external movements that are imposing a deformation level that would be similar to what a ground movement would cause. And so there's a couple of pieces. I won't get into it in too much detail. There is an ISO standard that's specific for ductile iron pipe, and in the United States we really wanted to open that up to any type of pipe material to be able to work in and be classified into the system so that we know what type of pipes work well in what type of areas. And so we can kind of split up our seismic design when we're talking about pipe systems into two general categories. We have the demand, or what the ground is going to impose onto the system. And we can talk about that in terms of axial ground strain or transverse ground strain. And then the second part of that is the capacity. So what is the capacity of the system, and how does that relate to the demand that is going to be imposed onto it? And so as we work through talking about sort of the demand side, that's something that it was existing, that we're developing through our American Society of Civil Engineers Task Committee for the manual practice on water and wastewater, seismic design of water and wastewater pipelines. There's a number of chapters in that, which Dr. Davis has been a certain leader, and I guess I've been more involved over time as we've gone through. And that is really aimed at kind of putting together a prescriptive design method in which you have certain systems that work for certain areas. There are tables and charts that make it as simple as it can be to have products that would work in different areas. And that's about 80% of the types of pipelines we want to design in seismic areas. And then there's some site-specific, when you have larger diameter or more critical systems, that we'd want to get into a little bit more detail. And so that's sort of how the MOP is, in a very, very short overview of what it looks like. And then part of that is this seismic design standard, and we're really excited to be moving this forward. I have a master's student, Jessica Ramos, who's our executive administrator for it, and I'm the committee chair. And Craig's actually the vice committee chair, right, for it. And we're looking at a couple of different pieces to try to standardize the process of assessing these things. And the reason why I think it's important for this group here is that as people are thinking about bringing new products into the United States, this is what we're hoping to eventually have established, so that different systems can be tested to the same sort of level of, to the same rigor, and that's sort of a standardized process. That's what we're working towards. So I'm going to go in and talk a little bit about this, the standard seismic testing and evaluation of pipeline systems, which has a good acronym. Something has a good acronym, it's got a chance, right? So we got it with a good acronym, and we got a chance for it to move forward. And it's a step in the right direction for what we want to accomplish with looking at the capacity of different pipeline systems for seismic response. This is a brief overview of sort of some of the chapters and what it looks like. I'll give a little bit of more detail about a couple of the chapters here, but in addition to what's in the standard, I think it's important to recognize there's a couple of things that are beyond the scope at this time. For instance, defining specific factors of safety would be a little bit beyond the scope of what this is doing. The idea is to be able to produce the test results, and then for the utilities and things to make informed decisions on what they would want to use in different areas. It doesn't include T's and elbows, service connections, torsion. It was a conversation we were having earlier today. So there's some things that it doesn't include, and I'm going to go over a couple of the pieces here that it does. And so when we think about pipeline systems and their ability to respond to ground movement, Professor O'Rourke did a great job of sort of setting this up in some examples. We can generally separate our systems into sort of two general categories. We have continuous pipelines, which would be welded or fused pipes. HDPE and steel would be examples of that. And they're generally going to respond to ground movement by strain in the pipe barrel. And so they're going to be able to move and respond. We also have segmented pipelines, or hybrid segmented pipelines, as we've started to call them now since some of the great work that was done at Cornell, where we have relatively very rigid pipes with somewhat flexible joints. And the idea is that these pipe joints are able to expand, lock into place, and transfer and translate movement to the next joint. The idea is sort of like a chain link response that we work towards. And then it gets a little trickier when we have things that are non-conformist style of pipes. So the example that Professor Rourke showed earlier would be this wave feature that's sort of analogous to a bendy straw, right? Where we are concentrating deformation at one feature that is weaker but is still continuous in nature and could be easily repaired following a large seismic event, for example. And another example of one that has a combined performance would be this plastic pipe where we're allowing this joint to open a certain amount, maybe 25 millimeters or something like that, and then it locks into place, and then it stretches. And that locking into place both takes into account the deflection in the joint, but also the strainability of the pipe material. This is a plastic material that's able to strain more, and so we're taking into account both of those positive attributes as we're trying to assess the systems, and that's what our testing methodologies are trying to get after. And one of the ways that we're getting after that, so we'll talk a little bit about compression too. Similarly, we can have different types of responses where we have pipes that will buckle but not leak, as an example. We'll have others that telescope inside, and we'll put them under many pressure cycles after they telescope and they still don't leak. And so there's different responses in compression, and we want to try to capture these things in our testing methodologies and standardize them the best we can. And so one of the ways that we do that is to design our tests in a way that provide a length of specimen that is adequate so that we're focused on this center portion, which we're calling the connection under investigation, the CUI. It could be a weld, it could be a joint, it could be a number of different things that we're interested in. And so providing the right type of length and sizing to these so that we don't have boundary effects is really important. It's something we talk about in our test setups, as well as looking at the instrumentation that we want to ensure that we provide the specimens, which I think my slide's out of order, but that's okay. Talk a little bit about transverse pipes, transverse bending. So a continuous pipeline will develop, will accommodate transverse loading through developing sort of a radius of curvature where you're getting axial tension on one side of the pipe and compressive strains on the other side of the pipe. We also have segmented pipelines where we concentrate the majority of the deflection really at the joints. And so this is an example of a test where that deformation is there. And then we have sort of this combined response. This is an example of a plastic pipe where we have some level of joint deflection here. We also have some level of curvature developing the pipe barrel. And so how do we measure and how do we take into account those different pieces and provide that information to be able to characterize the various systems? So for transverse bending, there's a number of things that we do when we set these tests up to be able to provide shear, a proper level of shear and a constant moment region for those of the structural engineers in the room. We use 4-point bending, which gives us an area where we have constant moment that we can measure pretty easily and interpret those results. We also provide rollers at the boundary conditions so that we have boundaries that aren't affecting sort of the performance and things that are going into it. And we'll use a number of different measuring techniques, including the use of string pots and other displacement measures to look at the response of the pipe and make that relative to a radius of curvature or curvature in the system. And the reason we've moved towards curvature for these is because we have this combined response where it's not always just the joint that's deflecting, which is talked about a lot of times, but when we talk about seismic, it's really the combination of all those pieces kind of working together. And so this would be an example of a test that we ran where we had a pretty significant level of curvature, and it's kind of hard to define what the angle is on this. There's an angle that's imposed, but it's really that curvature response that we're after and trying to measure. So when we look at our transverse bending test through the standard, another thing that we're trying to be careful of doing is how to set up the spacing and where you apply the loads and the reaction points along the pipe specimen. We give sort of a range in which that can be done. You can imagine that for very large diameter pipes, some of these things become quite challenging. For smaller diameter pipes, maybe it's a little bit easier. But the way that we're setting it up is that we have a preferred method, which would be somewhere between a 1/3 point and a 1/4 point loading system. And then there's also the opportunity to run finite element analysis and advanced methods to come up and justify the use of a different type of loading scenario if you have a large diameter or something that's not really conforming to sort of our standard setup. There are a couple of other sections that we have in here, material characterization, which is really referencing our ASTM standards, making sure that that's in the report because we know that the use of stress-strain data is really important in designing the test in the first place and then also interpreting the data later on. We've got a section on reporting the test results and examples of how you would interpret the data and what needs to be in there. And then we have some additional considerations that we've included that are sort of a little bit helpful to folks in thinking about how to design these things. For instance, what internal pressure would you run a test at? All of the testing we've done has been run in the range of 60 to 80 psi of water pressure. Is it necessary to do these types of tests at your highest water pressure? I would argue no. It would be best to run them at a representative water pressure at which you would think would be the water pressure during a seismic event, rather than something that's too high or no pressure at all, because it's really important that we capture the leakage or other types of responses throughout the course of each experimental procedure. So there's the last part of the standard is looking at some additional testing protocols. We talk about a couple of the other ones that we've done. We don't require them. This is a non-mandatory part of the standard. We talk about cyclic testing, where you might go back and forth in tension and compression over time to try to get an idea of degradation of some of these systems. We talk about soil structure interaction, fault rupture, shake table testing, all things that could be done, but are sort of outside of the immediate scope of what we really wanted to focus in on. And the third one that we talked just a little bit about is biaxial testing, which is going to have me circle back around to this oblique crossing. So there's a couple of different ways we can look at combined loading, where we might have a combination of compression and bending, or pipe tension and bending, which could lead to a reduction in the capacity in either direction, depending on that orientation of fault rupture. And so one of the things we're working on the research side, trying to push things further and looking out beyond the standard and what might be something that would be useful to add to it in 5 or 10 years down the line, is performing biaxial testing in the lab. And I just wanted to share this video of the way that we're doing these tests, where we're pushing down on the pipe system and to apply a level of transverse bending, and then we're pulling in tension in this example to apply that axial force. And we're looking at how the interaction of these two loading mechanisms maybe changes the response to be a little bit more representative of what we might see under certain circumstances during an earthquake or another type of ground deformation. One thing I didn't get a chance to mention was about some of our instrumentation. This pipe here is coated in a white paint, and it has on the other side of it dots to set up for our DIC measurement system. So that's allowing us digital image correlation, which allows us to know the strain at all points within the pipe and the joint and the system, which has been a very fun thing to work on with the students. And then we also have strain gauges along the pipe length to measure localized strains on the pipe barrel, as well as displacement devices across the joints vertically in a number of different areas. And so we're working to try to standardize the measurement techniques we need to take to get that key information that allows us to systematically sort of classify these different systems for levels of ground. These are just a couple of other pictures, if my video didn't work out, of sort of showing the stages of these things. It's been quite a process, and Craig, that was a funny joke about throwing a bunch of references up with your name on them. Craig's name's on a lot of these too, okay? But it's been quite a process as this MOP has moved forward. These are all publications we've had to put out in the last 5 or 6 years here. To try to look at the demands, some of the analytical modeling, the soil structure interaction, the capacity, and then the testing. And so this is just a little bit about some of the testing we've been doing and trying to pull together to try to standardize some of these processes to be able to develop this, these design guidelines for the industry. There's a couple of other references there. To wrap up, I'd just like to thank you all very, very much for the opportunity to present. I'll also mention Jessica Ramos again, who is the master's student. A lot of this work is her master's defense, which she'll be defending soon, and those her thesis and other papers will be coming out soon, where you'll be able to get a lot more information. In the meantime, I have two websites down here. The University of Colorado Boulder website, where we have $1 project reports, and the one that Professor O'Rourke mentioned earlier, the Cornell Lifelines website, where there's a lot of the test reports and things that a lot of this work and the standard has been based off of for a number of years. And so there's a lot of great information there that I would encourage you guys to check out. With that, I will wrap up and just thank you all very much.